Hey guys, tonight we begin with a question that has no satisfying answer which, if you think about it, is exactly the kind of question worth asking before sleep. Somewhere between 13,000 and 4,000 years ago, depending on where you look, the woolly mammoth vanished from this earth. Not all at once, not in some dramatic apocalypse that the movies would have you believe. They disappeared slowly, population by population, island by island, until one day the last mammoth on Earth stood alone on a frozen rock in the Arctic Ocean, and then even that one was gone. We were there for most of it. Humans, I mean. We watched it happen. We may have helped it happen. And yet somehow, despite being witnesses and possibly accomplices, we still argue about what exactly went wrong. If you're new here, welcome. Consider subscribing if you enjoy falling asleep to stories about extinction, which says something about all of us that I won't examine too closely. Leave a comment telling me where you're listening from tonight. I'm always curious about the geography of insomnia, and if you've been here before, thank you for coming back. Dim the lights if you haven't already, maybe put on a weighted blanket, and let's talk about the largest land animals to walk the earth alongside our ancestors, and how they became nothing more than bones in permafrost and questions without answers. This is the kind of mystery that doesn't resolve. It only deepens the longer you look at it. Perfect for a night when you don't want endings, just the slow unfolding of something vast and sad and strange. Here is what I want you to consider as you drift. The mammoth did not simply die. It was erased from a world that had depended on it for millions of years. And the erasure happened so recently, in geological terms, that we can almost reach back and touch it. The bones are not fossils. Not really. They still have marrow. They still have DNA. Some of them still have flesh. We have found mammoths so well preserved that scientists have eaten their meat not because they should have, but because humans are like that. The mammoth is not ancient history. It is recent history that feels ancient because we have collectively agreed to forget how close we came to sharing the earth with giants. The conventional story goes something like this. The Ice Age ended, the climate warmed, the grasslands turned to forests and tundra, and the mammoths couldn't adapt. Or alternatively, humans arrived with spears and hunger, and we hunted them into oblivion. Both stories are partially true, which means both stories are partially false. The reality, as we'll explore tonight, is messier and more unsettling. It involves feedback loops, cascading failures, genetic bottlenecks, shifting ecosystems, and the uncomfortable possibility that there was no single cause, just a series of small disasters that accumulated until a species that had survived dozens of ice ages couldn't survive one more warming. What makes the mammoth disappearance so compelling, I think, is that it sits right at the edge of human memory. We painted them on cave walls, we carved them into ivory, we built houses from their bones, and then, within a few thousand years, they were gone, and the paintings became the only evidence that they had ever existed at all. The mammoth is the first extinction that we might have caused, the first time humanity looked around and noticed that something enormous was missing from the world. Whether we are guilty or merely coincidental, the question haunts us. It should. Because it turns out the mammoths were not just large animals. They were ecosystem engineers, climate regulators, and keystone species whose absence changed everything. When the mammoths disappeared, they took a world with them. Tonight, we're going to try to understand what that world was, why it ended, and what the silence they left behind still has to teach us about loss, responsibility, and the fragility of everything that seems permanent. The mammoth imagination. Before we talk about what killed them, let's talk about what they were, because the mammoth of popular imagination and the mammoth of scientific reality are not quite the same animal. When most people picture a mammoth, they see an elephant in a fur coat, shaggy, tusked, lumbering through snow, probably looking cold and miserable. This is not entirely wrong, but it misses the essential strangeness of the creature. The woolly mammoth, Mammothus primigenius, was not simply an elephant adapted to winter. It was a distinct species that had evolved over hundreds of thousands of years to thrive in an environment that no longer exists, the mammoth steppe. A vast grassland ecosystem that once stretched from Spain to Canada, from the Arctic Ocean to the mountains of Central Asia. We will talk more about the mammoth steppe later, because understanding it is essential to understanding what was lost. For now, just know that the mammoth was not an exile from warmer climates, huddling miserably in the ice. It was perfectly, exquisitely adapted to its world. The cold was not its enemy, the warmth was. The woolly mammoth stood about 9 to 11 feet tall at the shoulder, roughly the size of a modern African elephant, though with different proportions. Its skull was higher and more domed, its back sloped downward toward the hindquarters, and its ears were much smaller in adaptation to conserve heat. The trunk was shorter than an elephant's, with 2 finger-like projections at the tip for grasping grass and vegetation. The tusks were enormous, curving upward and inward, sometimes crossing over each other. Unlike elephant tusks, which are relatively straight, mammoth tusks could spiral dramatically, reaching lengths of over 13 feet in some individuals. We found tusks so large that it's difficult to imagine how the animal could have carried them. The answer, apparently, is that old males sometimes couldn't. The tusks kept growing throughout their lives, becoming progressively more unwieldy, until some elderly mammoths must have walked around with what amounted to bone furniture attached to their faces. And then there was the fur. The woolly mammoth had a double coat, a dense undercoat of fine woolly hair for insulation, and an outer coat of longer guard hairs that could reach over 3 feet in length. We know this not from inference or reconstruction, but from actual preserved mammoth hair which still exists in remarkable quantities. The colour was likely reddish-brown to dark brown, though it bleached over time in preserved specimens. Some mammoth hair has been DNA tested and found to contain genes for lighter coloration, suggesting that mammoths, like many animals, varied in their appearance. They also had a thick layer of subcutaneous fat, small ears to minimise heat loss, and a tail so short it was almost vestigial. Everything about the woolly mammoth was designed for cold. The irony, as we'll see, is that cold was exactly what disappeared. But here's what the popular imagination misses most. The woolly mammoth was only one species in a diverse family. The mammoth lineage, Mammoths, included at least a dozen species spread across Africa, Europe, Asia, and North America. There were small mammoths and enormous mammoths, tropical mammoths and temperate mammoths, mammoths adapted to grasslands and mammoths adapted to forests. The Columbian mammoth, Mammuthus columbi, roamed North America and was even larger than the woolly mammoth, with less fur and straighter tusks. Standing around 13 feet at the shoulder and weighing up to 10 tons, the Columbian mammoth was a giant even among giants, adapted to the warmer grasslands and forests of what is now the United States and Mexico. The steppe mammoth, Mammothus trogontheri, was the largest of all, standing over 14 feet at the shoulder, a true giant among giants. There were dwarf mammoths on Mediterranean islands and dwarf mammoths on Channel Islands off the coast of California, separate populations that evolved small size independently because island life favours the economical. The mammoth was not one story but many stories, each population adapting to local conditions, each extinction a separate tragedy with its own causes and timing. When we ask what killed the mammoths, we are really asking a dozen different questions, and the answers don't always match. What we can say with certainty is this: for millions of years, some species of mammoth lived almost everywhere that wasn't tropical. They were among the most successful large mammals in Earth's history. And then, in a geological eye blink, they were all gone. Every species, every population, every last individual. The question is not just why they died, but why they died so completely, so quickly, and so recently that we almost remember it. The architecture of a mammoth. Let us look more closely at the body of the beast, because the details matter more than you might expect. A mammoth's tusk was not just a weapon or a display. It was a tool, a calendar, and a biography written in ivory. Mammoth tusks grew continuously throughout life, adding new layers of dentin in daily, weekly, and yearly cycles, much like tree rings, but far more detailed. Scientists can read these layers to reconstruct the life history of individual mammoths with astonishing precision. A 2021 study analysed the tusk of a male mammoth named Kik, who died in Alaska about 17,000 years ago. By measuring isotope ratios in successive layers of his tusk, researchers tracked his movements week by week throughout his 28-year life. They could see when he was weaned from his mother, when he left his family herd, when he travelled hundreds of miles across the landscape, and when he finally died, probably from starvation during a harsh winter, based on the isotope signatures in his final tusk layers. One animal, dead for 17 millennia, and we know his life story better than we know the lives of most medieval kings. The isotope analysis revealed something else about Kik's life. He was a wanderer. Over his lifetime, he walked enough miles to circle the earth twice. This was not unusual. Mammoths were migratory animals, following the seasons across vast territories in search of food and water. The males, in particular, ranged widely after reaching maturity, driven by the need to find mates and the competitive pressure from other males. This behavioural pattern, familiar to us from modern elephants, meant that mammoth populations were interconnected across enormous distances. Genes flowed freely. Local extinctions could be reversed by immigration. The mammoth's world was large and unified, at least until it wasn't. The social structure of mammoth herds was almost certainly similar to that of modern elephants, because we are primates and cannot help but see ourselves in everything. The herds were matriarchal, led by the oldest and most experienced female. Her knowledge of water sources, of seasonal routes, of dangerous areas was crucial to the survival of the group. Young mammoths stayed with their mothers for years, learning the landscapes and the rhythms of mammoth life. Males eventually left to join bachelor groups or to wander alone, returning to female herds only for mating. This social structure, which works beautifully when populations are large and landscapes are continuous, becomes a liability when populations fragment and habitats shrink. A matriarch's knowledge is only useful if the places she knows still exist. The mammoth's digestive system was a marvel of inefficiency that somehow worked. Like modern elephants, mammoths were hindgut fermenters, meaning they digested plant material in their large intestine rather than in specialized stomach chambers like ruminants do. This made them less efficient at extracting nutrients from food, but it allowed them to eat a wider variety of plant material and to process food quickly. A mammoth could eat several 100 pounds of vegetation per day and still be hungry. This constant need for food drove their migration patterns, their habitat requirements, and ultimately their vulnerability. When the vegetation changed, the mammoths could not simply switch to a new diet. They were committed to a way of eating that depended on a way of living, that depended on a world that was disappearing, the world they made. To understand the mammoth's disappearance, you must first understand the mammoth's presence, and this is where things get complicated in ways that no one fully anticipated until recently. For most of the 20th century, scientists thought of mammoths as passive inhabitants of the Ice Age landscape creatures that happened to live in the mammoth steppe, like furniture that happened to sit in a room. The steppe existed, the mammoths lived on it, and when the steppe disappeared due to climate change, the mammoths disappeared with it. Simple cause and effect. The environment shaped the animal. But research over the past few decades has increasingly suggested that the relationship ran both ways. The mammoths didn't just live on the steppe, they created it. Or at least, they maintained it. This is the concept of the megafaunal ecosystem engineer, and it changes everything about how we understand both the mammoth's life and the mammoth's death. Here's how it worked. The mammoth steppe was a grassland, not a forest or a tundra bog. Grass needs certain conditions to outcompete trees and shrubs. It needs disturbance, nutrient cycling, and something to prevent woody vegetation from taking over. In modern grasslands, fire often plays this role. In the mammoth steppe, the mammoths themselves were the disturbance. A single mammoth could eat several 100 pounds of vegetation per day. A herd of mammoths moving across the landscape would trample shrubs, knock down small trees, tear up moss and compact snow in winter, exposing the grass beneath and fertilizing it with enormous quantities of dung. The mammoths were not grazing on the steppe, they were gardening it, maintaining the conditions that allowed grass to thrive. This matters because grass and forest have very different relationships with climate, particularly in the Arctic. The mammoth steppe was not just different vegetation, it was a different climate regime. Grasslands reflect more sunlight than forests, keeping the ground cooler in summer. In winter, mammoth-trampled snow was thinner and denser, allowing cold air to penetrate the soil and keeping the permafrost frozen. When the mammoths disappeared, the grasslands began converting to shrubland and tundra bog. The new vegetation absorbed more heat, The untrampled snow insulated the ground, and the permafrost began to warm. The mammoths had been a cooling mechanism. Their absence was a warming mechanism. This is the feedback loop that makes the mammoth extinction so difficult to untangle. Climate change may have killed the mammoths, but the death of the mammoths may have accelerated climate change. Which came first? Did warming reduce the mammoth population, which reduced their ecosystem engineering, which allowed more warming, which killed more mammoths? Or did something else reduce the mammoth population, which destabilized the steppe, which caused local warming regardless of global climate trends? The answer is probably yes to all of the above, in different proportions at different times and places. This is not satisfying, but extinction is rarely satisfying. It's a cascade, not a cause. The modern implications of this feedback loop are sobering. The permafrost that covers much of Siberia and northern Canada contains vast amounts of organic carbon, the remains of plants and animals that accumulated over tens of thousands of years. As long as the permafrost stays frozen, this carbon stays locked away. But as the permafrost thaws, a process accelerating today due to climate change, microbes begin decomposing this organic material, releasing carbon dioxide and methane into the atmosphere. Some researchers estimate that permafrost contains twice as much carbon as is currently in the atmosphere. If even a fraction of this carbon is released, it could dramatically accelerate global warming. The mammoths, by maintaining cold grasslands and keeping permafrost frozen, may have been holding back this carbon reservoir. Their extinction may have begun a slow-motion carbon bomb that is still detonating today. The laboratory in Siberia. The Russian scientist Sergei Zimov has spent decades testing this theory at Pleistocene Park in northeastern Siberia, where he has introduced bison, horses, musk, oxen, yaks, and other large herbivores to see if they can recreate the mammoth steppe ecosystem. The park began in 1996, and what started as a seemingly quixotic experiment has become one of the most important long-term ecological studies in the world. The early results are promising and disturbing in their implications. The animals do indeed trample shrubs, compact snow, and maintain grassland. Winter soil temperatures in areas with large herbivores are significantly colder than in adjacent areas without them, because the trampled snow allows cold air to reach the ground. The grasslands that emerge support more biodiversity than the shrublands they replace. Zimov's experiment proves that mammoths mattered. It also proves that they cannot be replaced. There's a limit to what modern animals can do. None of them are mammoths. None of them have the size, the numbers, or the millions of years of coevolution with the steppe ecosystem. Bison and horses can do some of what mammoths did, but not all of it. The mammoth's sheer bulk, its ability to knock down trees, to break through snow crusts, to travel enormous distances while spreading seeds and nutrients cannot be replicated by any living animal. Zimov works closely with scientists at Colossal Biosciences, the company attempting to resurrect the mammoth through genetic engineering. The collaboration makes a certain sense. If you want to restore the mammoth steppe, eventually you need mammoths. But Pleistocene Park serves a more immediate purpose than waiting for de-extinction. It demonstrates, in real time and at meaningful scale, that ecosystems are not static. They are maintained by the creatures that inhabit them, and when those creatures disappear, the ecosystems change. This seems obvious, but it is not how we typically think about landscapes. We tend to imagine that the Arctic tundra has always been tundra, that the Siberian forest has always been forest, that the way things are is the way things have been. Zimov's work shows that the current landscape is a ghost landscape, the aftermath of an extinction, not a natural state. We are living in the ruins of the mammoth's world, and we have mistaken the ruins for the original. The climate case. Let's examine the evidence for climate as the primary cause of mammoth extinction, because it is substantial and deserves to be taken seriously, even if it's not the whole story. The mammoth had survived ice ages before. This is crucial to remember. The Pleistocene epoch, which began about 2.6 million years ago and ended about 11,700 years ago, he was not one continuous ice age, but a series of glacial and interglacial periods, cold spells and warm spells, alternating in roughly 100,000-year cycles, driven by variations in Earth's orbit. During glacial periods, ice sheets advanced, sea levels dropped, and the mammoth steppe expanded. During interglacial periods, the ice retreated, seas rose, forests spread northward, and the mammoth steppe contracted. The mammoths had lived through dozens of these cycles. They had survived interglacials warmer than the current one. Why would the most recent warming be any different? This is the question that climate-focused researchers have worked hard to answer, and they have found some compelling evidence. First, the most recent deglaciation was unusually rapid and severe in certain regions. The ice sheets collapsed faster than in previous cycles, and the resulting meltwater pulses dramatically altered ocean circulation and regional climates. The mammoth steppe didn't just shrink, it fragmented into isolated patches separated by expanding forests, wetlands, and tundra. Mammoths in different regions found themselves cut off from each other, unable to migrate or interbreed. Genetic studies of mammoth DNA show exactly this pattern. Declining diversity, increasing inbreeding, and population fragmentation in the final millennia before extinction. A major 2021 study published in Nature analysed environmental DNA from Arctic sediments spanning the last 50,000 years. By extracting and sequencing DNA fragments preserved in ancient soils, researchers could track changes in plant communities and animal populations over time. The results supported the climate hypothesis. Mammoth populations crashed in lockstep with vegetation changes, as the nutrient-rich grasses of the mammoth steppe gave way to less nutritious shrubs and mosses. The study suggested that mammoths simply ran out of food as their habitat transformed beneath their feet. Second, the warming affected not just temperature but precipitation patterns. The mammoth steppe was cold but dry, a polar desert that received less snow than modern tundra. As the climate warmed, precipitation increased, and the dry steppe became boggy wetland. Mammoths could handle cold. They could not handle deep snow and waterlogged ground that made it difficult to move, difficult to find food, and difficult to maintain the trampling and grazing that kept the steppe alive. The ecosystem was shifting underneath them, literally, as permafrost melted and the ground became unstable. Third, the vegetation itself was changing in ways that reduced mammoth food quality. The mammoth steppe was dominated by grasses, sedges, and herbs, nutrient-rich plants that could support megafaunal populations. As forests advanced and tundra spread, these gave way to shrubs, mosses, and lichens plants with lower nutritional value and higher chemical defenses. A mammoth could survive on tundra vegetation, but it couldn't thrive on it. Populations would have been under constant nutritional stress, reducing reproduction rates and making individuals more vulnerable to disease, predation, and environmental shocks. The climate case is strong, but it has a fatal weakness: timing. If climate change alone killed the mammoths, they should have disappeared everywhere at roughly the same time when the steppe collapsed. Instead, the extinction was staggered. Mammoths disappeared from Europe around 14,000 years ago, from most of North America around 11,000 years ago, from mainland Siberia around 10,000 years ago, but survived on Wrangel Island until about 4,000 years ago, and on Paul Island in Alaska until about 5,600 years ago. The climate on Wrangel Island was no different from the surrounding mainland. The vegetation was no better. So why did the Wrangel mammoths persist for 6,000 years after their continental relatives had died? The answer seems to be that Wrangel Island had something the mainland lacked: an absence of humans. The mammoths survived wherever humans hadn't arrived yet, and they died within centuries of human arrival. This pattern is too consistent to be coincidence. Climate set the stage, but something else struck the final blow: the human case. Now we must talk about ourselves, which is always uncomfortable when the subject is extinction. Humans arrived in the Americas somewhere between 20,000 and 15,000 years ago, depending on which archaeological evidence you find most convincing. The exact timing is contentious. There are sites that might be earlier, claims that are disputed, and a general sense among archaeologists that the Clovis first model of human migration has collapsed without a clear consensus on what should replace it. But what's not contentious is that humans and mammoths overlapped in the Americas for at least several thousand years. Long enough for humans to learn mammoth behavior, mammoth migration routes, mammoth vulnerabilities. Long enough to develop specialized hunting techniques. Long enough to carve mammoth images, tell mammoth stories, and incorporate mammoths into cultural life. and then the mammoths were gone. The overkill hypothesis was most famously articulated by the paleontologist Paul Martin in the 1960s, and it remains influential though controversial. Martin argued that humans, arriving in a landscape where the large animals had never encountered sophisticated predators, found easy hunting. The megafauna were naive. They didn't know to fear humans, didn't know to flee, didn't know that the small bipedal creatures were dangerous. Humans exploited this naivety with devastating efficiency, hunting mammoths, mastodons, ground sloths, and other megafauna faster than the animals could reproduce. Within 1,000 years of human arrival in any new territory, the megafauna collapsed. This pattern holds for the Americas, for Australia, for Madagascar, for New Zealand. Everywhere humans arrived, the large animals disappeared shortly after. The correlation is too strong to ignore. The archaeological evidence for mammoth hunting is real, if sparse. Clovis points the distinctive fluted stone tools that appeared in North America around 13,000 years ago have been found in association with mammoth remains at multiple sites. A 2022 study from Texas State University used experimental archaeology to test whether Clovis points could effectively penetrate mammoth hide and reach vital organs. The researchers created replica Clovis points and used them against elephant carcasses from animals that died naturally. The results confirmed that Clovis points were capable of killing mammoths when properly placed. A thrust between the ribs could reach the heart or lungs. The study concluded that Clovis points were indeed effective weapons, not just butchering tools. But critics of the overkill hypothesis point out that we have surprisingly little direct evidence of mammoth hunting. Kill sites exist, places where humans clearly butchered mammoths, but they are rare compared to what we would expect if humans were systematically hunting mammoths to extinction. Where are the millions of bones with cut marks? Where are the mass kill sites, the drive lanes, the evidence of industrial-scale slaughter? The Clovis people left behind beautiful fluted points, some of which are found with mammoth remains, but the numbers don't add up to an extinction event. Unless, of course, you don't need to kill that many. This is the key insight that makes overkill plausible, even without massive kill sites. Mammoths reproduced slowly. Like modern elephants, they probably had gestation periods of around 22 months, weaned their young for several years, and didn't reach sexual maturity until their teens. A female mammoth might produce only 4 or 5 calves in her lifetime. This means that even a modest increase in mortality, a few extra deaths per year per population, could tip the balance from population stability to population decline. You don't need to kill every mammoth. You don't even need to kill most mammoths. You just need to kill slightly more than can be replaced. Compound that over centuries, and extinction becomes inevitable even with relatively low hunting pressure. The math is grim but simple. If a population of 10,000 mammoths produces 500 calves per year, and natural mortality takes 400 of those before they can reproduce, the population is stable with only 100 individuals reaching reproductive age. But if humans kill an additional 100 individuals per year, just 1% of the population, no calves reach reproductive age, and the population begins to decline. Over a few centuries, the population crashes. Over 1,000 years it's gone, and 100 mammoths per year is not very many. A tribe of a few hundred people could easily take that many without ever feeling like they were hunting intensively, without ever leaving the kind of kill sites that archaeologists would expect. Death by 1,000 small cuts, not death by massacre. The other factor humans introduced was competition for resources. Early Americans were not just hunting mammoths, they were hunting everything. Bison, elk, deer, rabbits, birds. They were gathering plants, fishing, burning landscapes to improve hunting conditions. Every animal a human ate was an animal unavailable to other predators. Every plant a human gathered was a plant unavailable to herbivores. The arrival of humans didn't just add a predator to the ecosystem, it reorganized the entire energy flow. Mammoths, already stressed by climate change and habitat fragmentation, now had to compete with a new, highly efficient omnivore for diminishing resources. The combination was lethal. And yet, the human case has its own weaknesses. Humans lived alongside mammoths in Siberia for tens of thousands of years without hunting them to extinction. The Siberian mammoths died out only after the climate shifted and the steppe collapsed. If humans were capable of hunting mammoths to extinction, why did it take so long in Siberia but happen so quickly in the Americas? The answer might be population density. There were simply more people in the Americas during the critical period, or hunting technology. Clovis points were more efficient than earlier tools, or some combination of factors that made the American situation uniquely deadly. But the pattern is not as clean as the overkill hypothesis suggests. Humans and mammoths coexisted for millennia in some places and for centuries in others. The extinction was not instantaneous or uniform. It was, like the climate case, a cascade of factors that accumulated until the system collapsed. The synergy theory. Perhaps the most honest answer to what killed the mammoths is everything at once. This is the synergy hypothesis, and it has gained traction because it explains patterns that neither climate nor overkill can explain alone. The idea is simple. Mammoths could survive climate change without human pressure, and they could survive human pressure without climate change, but they could not survive both simultaneously. The two stressors were individually manageable but collectively lethal. Think of it in terms of resilience. A healthy mammoth population spread across a large connected habitat with abundant food and normal reproduction rates can absorb considerable losses. Hunters take some individuals. The population compensates by producing more calves or by individuals dispersing from high-density areas. Climate shifts reduce habitat. The population contracts to remaining suitable areas and maintains genetic diversity through migration. But a population already stressed by climate change, fragmented, inbred, nutritionally marginal, cannot also absorb hunting pressure. And a population already reduced by hunting small, isolated, with disrupted social structures cannot also adapt to rapidly changing climate. The two factors amplify each other. Climate makes hunting more destructive. Hunting makes climate change more deadly. There's evidence for this synergy in the genetic record. Ancient DNA extracted from mammoth remains shows that populations went through severe bottlenecks, periods when genetic diversity crashed because only a small number of individuals survived to reproduce. These bottlenecks correlate with climate fluctuations, but they become more severe and more frequent toward the end, suggesting that something was preventing populations from recovering. Climate stress followed by hunting pressure, followed by climate stress, followed by more hunting each cycle, reducing the population's ability to bounce back until there was nothing left to bounce. A particularly elegant study published in 2021 modeled the interaction between climate and human factors using simulation techniques. The researchers found that neither factor alone could account for the observed extinction pattern across different mammoth populations. Climate change explained why mammoths disappeared from some areas but not others. Human hunting explained why mammoths failed to recolonize areas where the climate had become suitable again. Together, the two factors trapped mammoth populations in a vise. Climate change squeezed them into shrinking refugia, and human hunting prevented them from escaping or recovering. The simulation predicted extinction timelines that closely matched the actual archaeological and paleontological record. This synergy theory is unsatisfying because it doesn't give us a single villain. We want to blame climate or humans, nature or ourselves. But extinction doesn't work that way. It works through accumulation, through the piling up of small disadvantages until the system can no longer compensate. The mammoth extinction was not a murder mystery with a single culprit. It was a tragedy of compounding failures, any one of which might have been survivable, all of which together were not. The island laboratories. Islands are nature's experiments, and the islands where mammoths made their last stands tell us things we couldn't learn anywhere else. Wrangel Island. We've discussed a frozen rock in the Arctic Ocean, about the size of Yellowstone National Park, where mammoths survived until the Egyptian pyramids were being built. Let that sink in for a moment. When Khufu's architects were designing the Great Pyramid, the last mammoths were still alive on a windswept island in the Arctic. The overlap is not metaphorical, it is literal. Mammoths and pyramids coexisted on planet Earth. The species we think of as ancient, as Ice Age relics, as prehistoric, survived well into the historical period. We just weren't paying attention because we were busy building civilizations in the wrong part of the world. The Wrangel Island population is particularly well studied because of recent advances in ancient DNA analysis. A 2024 study published in Cell analysed 21 mammoth genomes spanning the last 50,000 years of the species' existence. The results painted a detailed picture of the Wrangel population's history. About 10,000 years ago, a tiny group of mammoths, perhaps as few as 8 individuals, became isolated on Wrangel as rising sea levels separated the island from the Siberian mainland. This founding population was genetically impoverished from the start, carrying only a small fraction of the genetic diversity present in the original mammoth population. Over the next 6,000 years, the Wrangel mammoths persisted in surprising stability. The population grew to between 200 and 300 individuals and maintained that level for millennia. They showed clear signs of inbreeding. The genetic signatures of mating between relatives accumulated steadily over time, but the inbreeding did not immediately doom them. The population accumulated harmful mutations, including genes that affected their sense of smell and possibly their coat coloration. But these mutations were not lethal. The Wrangel mammoths were sick, genetically speaking, but they were not dying. This finding overturned the previous assumption that genetic deterioration caused the Wrangel extinction. If inbreeding was killing the mammoths, we would expect to see accelerating decline in the final centuries as accumulated mutations reached critical levels. Instead, the population appears to have been stable right up until the end. Something else killed them, possibly a random environmental catastrophe like a severe storm or drought, possibly disease, possibly even the arrival of humans. Though no clear evidence of human presence on Wrangel has been found from the extinction period, the 2024 study concluded, somewhat anticlimactically, that we still don't know what killed the last mammoths. We know what didn't kill them, inbreeding depression alone, but the final cause remains mysterious. But Wrangel was not the only island refuge. St. Paul Island, in the Bering Sea between Alaska and Russia, hosted mammoths until about 5,600 years ago. This population is particularly interesting because we have high-resolution evidence for what killed them: drought. Sediment cores from a lake on Strait. Polls show that freshwater availability declined dramatically in the centuries before extinction. As sea level rise shrank the island and saltwater contaminated the aquifer. The mammoths, like all large animals, needed substantial amounts of fresh water, perhaps 20 gallons per day. As the lake shrank and fresh water became scarce, the population collapsed, not hunting. Not habitat change. Simple thirst. The St. Paul extinction demonstrates how local and specific the causes of mammoth death could be. An island population is at the mercy of island conditions. Changes that would be insignificant on a continental scale become lethal when there's nowhere to migrate. The Wrangel and Street. Paul mammoths survived climate change that killed their mainland relatives, but they couldn't survive the particular challenges of their isolated habitats. Size matters. Connectivity matters. The factors that allowed island populations to persist isolation from human hunters, stable local conditions, were the same factors that made them vulnerable when conditions changed. There's also the strange case of the Channel Islands mammoths off the coast of California. These were not woolly mammoths, but Columbian mammoths that became dwarfed through island evolution, standing only about 5 to 6 feet tall at the shoulder, roughly a third the size of their mainland ancestors. They arrived during the last ice age, when sea levels were lower and the islands were closer to the mainland, possibly even connected by land bridges or easily accessible by swimming. Once isolated, they evolved smaller body sizes over thousands of years, the classic island dwarfism that affects many large animals in resource-limited environments. The Channel Island mammoths went extinct around 13,000 years ago, roughly when humans first arrived in the region. Coincidence? The pattern suggests not. What the island mammoths teach us is that extinction is not one process but many. Continental extinctions, island extinctions, climate-driven extinctions, human-driven extinctions, thirst-driven extinctions, each follows its own logic, each leaves its own evidence, each tells its own cautionary tale. The mammoth didn't have one death. It had dozens of deaths, spread across time and space, each removing another piece of a species that had once been everywhere. By the time the last mammoth on Wrangel Island drew its final breath, mammoth extinction had been happening for 10,000 years. It was not an event, it was a process, and when it finally ended, there was no one left to mark the occasion. The the sinkhole trap. Sometimes the earth itself became a mammoth's enemy, and the evidence of this is preserved with remarkable clarity at a site in South Dakota. The mammoth site at Hot Springs was discovered in 1974 when a construction worker named George Hansen, preparing ground for a new housing development, unearthed bones that turned out to be something extraordinary. What had been planned as a subdivision became one of the most important paleontological sites in North America. The site preserves a natural sinkhole that formed about 140,000 years ago when an underground limestone cave collapsed, creating a steep-sided pit that filled with warm spring water. The warm water would have been irresistible to mammoths, especially during harsh winters. They came to drink, and many of them never left. The sides of the sinkhole were too steep and slippery for the mammoths to climb back out. Once an animal fell in, it was trapped. Over centuries, mammoths continued to be lured by the warm water and continued to die. As of the most recent counts, the remains of over 60 mammoths have been excavated from the site, 58 Columbian mammoths and 3 woolly mammoths. This mix of species is itself interesting. It suggests that the Hot Springs area was an ecological boundary zone where the ranges of both species overlapped. The site also contains the remains of other animals that met the same fate: giant short-faced bears, wolves, a camel, and numerous smaller creatures. What makes the mammoth site particularly valuable is its preservation. The bones were not scattered by scavengers or tumbled by rivers. They lie more or less where the animals died, accumulating layer upon layer over thousands of years. Visitors to the site today can watch ongoing excavation from elevated walkways, seeing the bones emerge from the sediment in something close to their original positions. It is one of the few places in the world where you can witness paleontology happening in real time, where the past is literally being uncovered before your eyes. There's something poignant about the mammoth site, beyond its scientific value. These animals died one at a time, over generations, each one making the same mistake. Perhaps they saw the bones of their predecessors in the water. Perhaps they didn't notice, or didn't understand, or simply couldn't resist the warmth. The trap kept working because mammoths kept falling for it. In a way, the sinkhole is a metaphor for extinction itself, a gradual accumulation of individual deaths, each one seemingly insignificant, until one day you look around and realize that something enormous is gone. What the bones remember. Let me tell you about what we've found, because the evidence of mammoth existence is not distant or abstract. It is abundant, tangible, and sometimes disturbing in its intimacy. The permafrost of Siberia and Alaska has preserved mammoths with a fidelity that seems almost unfair to the mammoths, who cannot benefit from our fascination, and unfair to paleontologists who study other extinct species and must make do with bare bones. We have mammoth skin. We have mammoth hair. We have mammoth blood, still liquid in some cases when the specimens were first discovered. We have mammoth stomach contents, preserved grass and sedge that tells us exactly what a mammoth ate on the day it died 10,000 years ago. We have baby mammoths so perfectly preserved that scientists have named them, as if they were pets rather than specimens: Luba, Dima, Yucca. We have everything except living mammoths. The most famous discovery is probably Luba, a female calf found by a reindeer herder named Yuri Kudi in Siberia in 2007. She was about 1 month old when she died, roughly 42,000 years ago. Her body is so complete that scientists have studied her baby teeth, her internal organs. Her milk consumption traces of her mother's milk were still in her stomach, and the cause of her death she suffocated in mud, which also preserved her. Luba is, in a sense, the most thoroughly known mammoth in history. We know more about her brief life than we know about most mammoths that lived for decades. She has been CT scanned, DNA sequenced, and exhibited around the world. She is a scientific treasure and a memorial to a species that cannot be brought back no matter how much we learn about it. Dima, a male calf discovered in 1,977 inches, Siberia's Magadan region, was for many years the best preserved mammoth known. He died around 40,000 years ago at about 6 to 12 months of age, apparently from falling into a muddy pit and being unable to escape. His body retained skin, muscle, and internal organs, allowing researchers to study mammoth anatomy in unprecedented detail. Dima's stomach contents showed that he had eaten his mother's dung, a behavior common in modern elephant calves, who ingest bacteria from adult feces to colonize their own digestive systems. Even 40 millennia after death, we can observe the intimate details of mammoth development. Yucca, discovered in 2010, has become famous for a different reason: her brain. Preserved in the Siberian permafrost for approximately 39,000 years, Yucca's brain was remarkably intact, so intact that in 2019, scientists extracted cell nuclei from her tissue and transferred them into mouse egg cells. The nuclei showed biological signs of activity, with some cell structures beginning to form. The experiment did not create a living mammoth or even a living mammoth cell, but it demonstrated that cellular machinery could potentially be revived even after tens of thousands of years in permafrost. The implications for de-extinction research were obvious and exciting. The implications for what it means to be extinct were more troubling. But the bones themselves tell stories too. Mammoth skeletons are found across the northern hemisphere, from Spain to Virginia, from the British Isles to China. They are found in riverbeds where mammoths came to drink and sometimes drowned. They are found in tar pits, most famously at La Brea in Los Angeles, where mammoths became mired alongside saber-toothed cats, dire wolves, and ancient humans. They are found in caves, in lake beds, in the foundations of buildings and the cuttings of roads. The mammoth was so widespread for so long that its bones are practically a geologic layer, a stratum of the recent past. And then there is the ivory. Mammoth tusks were valuable in the Pleistocene and remain valuable today, a fact that has complicated mammoth science considerably. Tusks erode out of permafrost and riverbanks every year, particularly in Siberia, and legal ivory harvesting has become a significant industry. This is, in theory, good. Mammoth ivory provides an alternative to elephant ivory, reducing demand for poaching. In practice, it has created a grey market where elephant ivory is sometimes passed off as mammoth ivory, and where commercial collectors destroy scientific context in their rush to extract saleable tusks. The mammoth cannot be poached, but it can still be exploited. Even in death, even 10,000 years later, we cannot leave them alone. The bones remember what we would prefer to forget, that extinction is not clean, not distant, not something that happens to creatures fundamentally unlike us. The mammoth died like any animal dies, in mud, in water, in cold, in hunger, one individual at a time. The bones are not monuments, they are remains, and the difference between a monument and remains is that remains were once alive. The companions who fell, the mammoth did not disappear alone. It vanished alongside an entire community of megafauna, and the scope of this loss is difficult to comprehend without listing what was lost, so let me list it, because the accumulation matters. In North America, the end Pleistocene extinction claimed the mammoth, the mastodon, the 4 species of ground sloth, one of which, Megalonyx, was as large as an ox. The giant beaver, which weighed over 200 pounds and built lodges the size of small houses. The American lion, larger than any modern lion, and yes, there were lions in North America. The dire wolf, the short-faced bear, which stood over 11 feet tall when upright, and was probably the largest mammalian predator in Pleistocene North America. The saber-toothed cat, the scimitar cat, the American cheetah, the tapir, 3 species of horse. Yes, horses were native to North America before humans arrived, then went extinct, then were reintroduced by the Spanish. We'll come back to this. 3 species of camel, also native to North America, also extinct. The stag moose, the shrub ox, the helmeted musk ox, the giant armadillo, and many others. By one estimate, North America lost over 30 genera of large mammals at the end of the Pleistocene. Not 30 species, 30 genera, each containing multiple species. It was a biological catastrophe. South America was hit even harder. The continent had been isolated for millions of years, developing unique megafauna unlike anything in the north. Then the Isthmus of Panama formed, North American species invaded, and the great faunal interchange began. Some South American species thrived, many did not. And then humans arrived, and the extinction pulse that had swept North America continued southward. South America lost its ground sloths, including Megatherium, as large as an elephant, the largest land mammal in South America and one of the largest that ever lived, its glyptodonts, armadillo relatives, the size of Volkswagens, with bony shells that could be used as shelters by early humans, its toxodons and macrauchenia and native horses and giant rodents and saber-toothed marsupials. The fauna that Europeans encountered when they arrived in the 16th century was a remnant, an impoverished shadow of what had existed 10,000 years earlier. Australia tells a similar story, though the timing is different. Humans arrived in Australia perhaps 50,000 years ago, and within 10,000 years the megafauna were gone. Giant kangaroos and wombats, marsupial lions, giant monitor lizards, giant flightless birds. Madagascar, colonized only about 2,000 years ago, lost its giant lemurs, elephant birds, and pygmy hippos. New Zealand, colonized about 800 years ago, lost its moa and its Haast's eagle. The pattern is consistent across continents and islands. Wherever humans arrived, the large animals disappeared. The mammoth was not an exception, it was the rule. What did these extinctions mean for the ecosystems left behind? We are only beginning to understand. The dire wolves and saber-toothed cats that hunted mammoths, what happened to them when their prey vanished? They vanished too, obviously. But the question is whether they might have survived on smaller prey if the mammoths had not disappeared, or whether their extinction was inevitable once their ecological niche collapsed. The scavengers that fed on mammoth carcasses, the condors, the giant vultures, the carrion beetles, what did they eat when the megafaunal buffet closed? Some adapted, many did not. The plants that depended on megafaunal dispersal, the Osage orange, whose fruit is perfectly sized for a mammoth, but too large for any surviving animal, they still exist, producing fruit that falls to the ground and rots because the animal meant to eat it has been dead for 10,000 years. The ecosystem remembers what has been lost, even when we do not. This is the context for the mammoth extinction. Not an isolated event, but part of a global wave of extinctions that reshaped terrestrial ecosystems on every continent except Antarctica. We live in an impoverished world, and we have no idea what we're missing because we never saw what was there. The curious case of the horses. Here is a story within the story that illustrates how strange extinction can be. Horses evolved in North America. This is a scientific fact, though it runs counter to everything we associate with horses in the Americas. The first horses appeared in North America about 55 million years ago, and for tens of millions of years, the continent was the center of horse evolution. Horses diversified, migrated to other continents via land bridges, and became one of the most successful mammal lineages on Earth. By the Pleistocene, several species of horse roamed North America alongside mammoths and bison and all the other megafauna we've discussed. And then, about 10,000 years ago, all the horses in North America went extinct. Every species. The same wave of extinction that took the mammoths took the horses too. North America, the continent where horses had evolved and flourished for millions of years, became horseless. For the next 10,000 years there were no horses in the Americas. None. The indigenous peoples of the Americas developed their civilizations entirely without horses. No cavalry, no mounted hunting, no horse-drawn transportation. The bison hunting cultures of the Great Plains developed on foot, using dogs for transport. The great empires of Mesoamerica and South America built their cities and roads without draft animals larger than llamas. The absence of horses shaped American history in ways we can barely calculate. Then, in 1493, Christopher Columbus brought horses to the Caribbean on his second voyage. Spanish conquistadors brought more horses in subsequent expeditions. Within a century, escaped and released horses had established feral populations across the Americas. Within 2 centuries, indigenous peoples of the Great Plains had acquired horses and transformed their societies around them. The Comanche, the Lakota, the Cheyenne cultures that we now associate indelibly with horsemanship had been horseless for 10,000 years before European contact. The horse they adopted was a descendant of animals that had evolved in the Americas, gone extinct in the Americas, survived in Eurasia, and returned as an invasive species. The return of the horse to North America is sometimes called a rewilding, but this framing is contested. The horses that returned were not the same species that had gone extinct. 10,000 years of evolution in Eurasia had changed them. The ecosystems they returned to had changed too, adapted to horselessness, filled by other species, structured differently. Whether modern wild horses in the American West are native or invasive depends on how you define those terms and how far back your historical baseline extends. The mammoths cannot return the way the horses did. There are no mammoth populations surviving elsewhere that could be reintroduced, but the horse story shows that extinction is not always permanent, and that the boundary between presence and absence can be more permeable than we assume. Deep time, shallow memory. Here is something strange about human memory. We remember what we've lost only if we knew we had it. The mammoth existed alongside humans for tens of thousands of years. We painted it, carved it, hunted it, and almost certainly told stories about it. And then, when it was gone, we forgot. Not immediately, there are tantalizing hints that mammoth memory persisted in folklore and myth. The Khanty people of Siberia have legends of a great underground beast that dies when exposed to sunlight, a possible cultural memory of mammoth carcasses eroding from permafrost. Some scholars have suggested that giant bones found in antiquity contributed to myths of giants and dragons and cyclopes. The single eye socket of an elephant skull does look remarkably like a cyclops. If you don't know what an elephant is, but these are traces, fragments, half-remembered echoes. Within a few thousand years of extinction, the mammoth had passed from living memory into darkness. When Europeans first encountered mammoth bones in Siberia in the 17th and 18th centuries, they didn't know what they were looking at. Some thought they were the bones of giants mentioned in the Bible. Others thought they were the remains of elephants that had somehow wandered north and died. The notion that there had once been a cold-adapted elephant species, now extinct, was slow to develop because the concept of extinction itself was new and disturbing. If God had created all creatures, how could any creature cease to exist? Extinction implied imperfection in divine creation, a flaw in the system. It was theologically inconvenient and therefore difficult to accept. Georges Cuvier, the French naturalist, established the reality of extinction in the early 1800s by demonstrating that mammoth bones differed systematically from those of living elephants. In 1796, Cuvier presented a paper comparing the bones of modern African and Indian elephants with fossil bones found in Europe and Siberia. He showed that the jaw structure, the tooth patterns, and other anatomical features of the fossil animals were distinct from any living species. The mammoth was not a degenerate elephant or a displaced tropical species. It was something else, something that no longer existed anywhere on Earth. This was a profound shift in how humans understood nature. The world was not static. Species came and went. The past was different from the present, and not all differences could be recovered. But even after we understood that mammoths had existed and then ceased to exist, we struggled to understand what that meant. The mammoth became a symbol of the Ice Age, a mascot for a geological period, an image on museum walls and children's books. It became familiar in a way that obscured its strangeness. We domesticated the mammoth in our imagination, made it safe and friendly and long ago, placed it in a category of prehistoric that implied irrelevance to the present. The mammoth was over, done, finished. History had moved on. This is the failure of memory that I want to emphasize as you drift towards sleep. The mammoth is not ancient history. The pyramids are ancient history, and the mammoths outlived them. The mammoth extinction is recent history, recent enough that we might have prevented it if we had known what we were doing, recent enough that its effects are still rippling through ecosystems, recent enough that we can read the DNA and study the proteins and analyze the stomach contents. We have forgotten not because the mammoth was long ago, but because we choose to forget. We choose to place extinctions in the past so we don't have to think about the ones happening now. The mammoth is comfortable, the elephant is not. Consider that there are people alive today who remember when passenger pigeons still darkened the sky, when thylacines still prowled Tasmania, when Chinese river dolphins still swam the Yangtze. These extinctions happened within living memory, and already they are fading into the same comfortable distance as the mammoth. Give it another century and they will be prehistoric too. Relics of an earlier age, nothing to do with us, nothing we could have changed. Memory is short, extinction is long. The disconnect between the two is how we allow it to keep happening. The violence of remembering. There is another way that mammoths are preserved, in human culture, and this preservation is not always comfortable to examine. We know that Ice Age humans hunted mammoths because they told us so in paintings, in carvings, in the arrangement of bones at kill sites. The cave paintings at Rouffignac in France include over 150 mammoth images, more than any other animal represented at the site. Known as the Cave of the 100 Mammoths, Rouffignac contains some of the most detailed and numerous mammoth representations in prehistoric art. The paintings date to the Magdalenian period, around 13,000 years ago, when mammoths still walked the European landscape. The artists who painted these images knew mammoths. They had seen them alive, watched them move, studied their forms. The paintings are not imaginary reconstructions, they are portraits. The Chauvet Cave in southern France, even older than Rouffignac, contains mammoth images dating back perhaps 36,000 years. These are among the oldest known figurative artworks in the world, and mammoths feature prominently. One image shows a mammoth's head rendered with extraordinary skill, the domed skull, the small ear, the curve of the trunk captured in confident red ochre lines. Nearby, a human hand has been pressed against the cave wall, leaving a red outline that has lasted for 36 millennia. The juxtaposition is startling. Human hand, mammoth image, both preserved in darkness while the living creatures they represented went extinct outside. The carvings from Vogelherd in Germany, over 40,000 years old, include exquisite mammoth figurines rendered with evident skill and care. These tiny ivory carvings, some small enough to fit in a closed palm, show mammoths with the domed head, curved tusks, and distinctive shoulder hump that we recognize from preserved remains. The artists understood mammoth anatomy. They observed these animals closely enough to capture their essential features in miniature. These images are beautiful. They are also documents of violence. The humans who made them were predators contemplating prey. Some of the most famous mammoth representations show animals that are clearly being hunted. A carved bone from Malta in Siberia shows a mammoth with spiral lines on its body that some researchers interpret as representations of internal organs, a hunting diagram, essentially, showing where to strike for maximum damage. We cannot know for certain what these images meant to the people who made them, but the interpretation is not neutral. If we see the paintings as reverent depictions of noble animals, we are choosing one story. If we see them as hunting guides and trophies, we are choosing another. Both are probably true to some degree. Predators can respect prey. Hunters can love what they kill. The ambiguity extends to the mammoth bone structures found across Ice Age Europe and Asia. These are dwellings, or at least structures, built from mammoth bones, primarily skulls, jaws and tusks arranged in circular patterns. The most famous examples are from Mezherik in Ukraine, where 4 structures made from the bones of nearly 150 mammoths have been excavated. Recent radiocarbon dating has refined our understanding of these structures, showing that they were built around 18,000 years ago during some of the harshest conditions of the last ice age. The structures were not permanent homes but temporary shelters, used during the coldest periods and then abandoned. Were these homes? Ritual sites? Storage facilities? We don't know. What we know is that they required an enormous number of mammoth bones, more than any single hunt could provide. Either the builders accumulated bones over generations, or they killed mammoths systematically and in large numbers. Either way, the structures represent a significant investment in mammoth death. They are monuments to extraction. This is uncomfortable to contemplate because we want to believe that indigenous peoples lived in harmony with nature, that the ecological destruction we witness today is a uniquely modern phenomenon, that our ancestors knew something we have forgotten about sustainable living. There is truth to this. Pre-industrial peoples generally had lower environmental impacts than industrial ones, but it is not the whole truth. The archaeological record suggests that humans have been causing extinctions for as long as we have been human. The mammoth hunters did not intend to drive mammoths extinct. But intention is not exculpation. Impact is impact, regardless of intent. I am not saying this to condemn Ice Age peoples, who were doing what any intelligent predator would do when given access to abundant resources. I am saying this because the story of the mammoth extinction is, in part, the story of human nature, our capacity to exploit, our difficulty in restraining ourselves, our tendency to assume that resources will last forever until suddenly they do not. The mammoth hunters could not have known they were hunting the last mammoths. Neither can we when we fish the last tuna, or fell the last mahogany, or pave the last meadow. The pattern is consistent across millennia. We take until there is nothing left to take, and then we are surprised that it is gone. Ghosts in the genome. Let me tell you about the mammoths we can read, because science has given us tools that would have seemed miraculous a generation ago. The first mammoth genome was sequenced in 2008, from hair found preserved in Siberian permafrost. Since then, dozens of mammoth genomes have been sequenced, along with genomes from mastodons, Columbian mammoths, and even hybrids between woolly and Columbian mammoths. Yes, they interbred. The genetic data has transformed our understanding of mammoth evolution, population structure, and decline. It has also raised possibilities that would have been unthinkable to earlier generations of scientists. What the genomes tell us is a story of long success followed by rapid collapse. The mammoth lineage was genetically diverse for most of its history, with large populations spread across huge ranges, interbreeding and exchanging genes over tens of thousands of miles. Then, starting around 300,000 years ago, the populations began to decline, genetic diversity dropped, inbreeding increased. The decline accelerated dramatically during the last glacial cycle, and by the final millennia before extinction, the surviving populations were genetically impoverished, carrying accumulated harmful mutations that would have affected their health and reproduction. The Wrangel Island mammoths, in particular, show signatures of genetic deterioration. Loss of olfactory receptors meant they may have had reduced ability to smell, a significant disadvantage for an animal that relies heavily on scent to find food, detect predators, and communicate with other mammoths. Possible coat color abnormalities might have affected their ability to regulate body temperature. Other mutations affected genes involved in development and metabolism. They were not just dying out, they were falling apart. This genetic perspective adds another dimension to the extinction debate. Climate and hunting reduced populations below sustainable thresholds. But once populations were small enough, genetic factors began to matter too. Inbreeding depression, the reduced fitness that comes from mating with relatives, would have lowered reproduction rates and survival. Accumulated harmful mutations would have compromised health. The positive feedback loop that began with external pressures continued with internal pressures. Smaller populations became sicker populations, which became even smaller populations. By the end, extinction was probably inevitable regardless of external conditions, because the genetic damage was already done. This has implications for modern conservation. Species reduced to small populations face the same genetic risks the mammoths faced. If we save a species from hunting or habitat loss, but leave the population too small for too long, we may have only delayed the inevitable. The mammoth genomes are a warning. Survival is not just about numbers. It's about genetic health, about maintaining enough diversity for populations to adapt and recover. The mammoths that survived longest were the ones with the least genetic diversity. They were already dead, they just hadn't stopped moving yet. Recent advances have pushed even further into the mammoth genome. In 2024, scientists announced they had reconstructed the three-dimensional structure of a 52,000-year-old mammoth's genome, the first time this had been done for any ancient animal. The mammoth, found in Siberia's permafrost, had been freeze-dried so rapidly that its chromosomes were preserved in something like their original configuration. This allowed researchers to study not just which genes the mammoth had, but how those genes were organized and regulated. The findings suggested that mammoth genes were structured similarly to those of modern Asian elephants, their closest living relatives, another piece of evidence that de-extinction might be feasible, at least in principle. And then there is the question everyone asks about mammoth genomes. Can we bring them back? the resurrection business. The de-extinction of the woolly mammoth has moved from science fiction to science project over the past decade, and we should talk about what that means even if we cannot know how it will turn out. The basic idea is straightforward. Take the genome of a mammoth. Identify the genes that made it different from an elephant: cold tolerance, fat storage, small ears, shaggy hair, and edit those genes into an elephant genome. The resulting animal would not be a true mammoth, it would be an Asian elephant with mammoth-like features, but it would, in theory, be able to survive in Arctic environments and perhaps help restore the mammoth steppe ecosystem. The company leading this effort, Colossal Biosciences, was founded in 2021 by geneticist George Church of Harvard University and entrepreneur Ben Lamb. They have raised hundreds of millions of dollars and employ some of the most prominent scientists in genome editing and reproductive biology. They claim they will produce a mammoth-elephant hybrid within the next several years. George Church has been working on mammoth de-extinction since before Colossal existed. He began studying mammoth genomes in 2008 and has spent years identifying the key genetic differences between mammoths and elephants. His team has identified around 60 genes that appear to be responsible for mammoth adaptations to cold environments, including genes affecting hair growth, fat storage, and hemoglobin, the oxygen-carrying protein in blood, which in mammoths was optimized to release oxygen at low temperatures. Using CRISPR gene editing technology, Church's lab has successfully inserted some of these mammoth genes into elephant cell cultures, creating cells with mammoth-like traits. The progress has been incremental but real. In 2024, Colossal announced that it had created elephant cells with mammoth-like characteristics, including changes to genes affecting ear size and fat deposition. In 2025, the company reported engineering mice with mammoth hair genes, producing rodents with longer, woollier coats than normal. These are proof-of-concept experiments, not mammoths, but they demonstrate that the genetic editing approach can work in living organisms. The technical challenges are still significant. We have mammoth genomes, but genomes are not organisms. To make a mammoth, you need to turn those genes into a living embryo, implant that embryo in a surrogate mother, and bring it to term. Elephant pregnancies last nearly 2 years. Elephant reproduction is notoriously difficult to manage even under normal circumstances. Elephant-mammoth hybrids have never been attempted and might not be viable. And even if a calf is born, it needs to learn mammoth behaviors, migration patterns, social structures, foraging strategies that no living animal can teach it, because no living animal remembers them. The mammoth knowledge died with the last mammoths. We can reconstruct the body, but not the culture. There are also ethical questions that tend to get less attention than the technical ones. Is it right to create an animal that has never existed, neither mammoth nor elephant, but some novel hybrid, and release it into an environment where it has no parents, no herd, no evolutionary history? What obligations do we have to such a creature? If it suffers from unforeseen genetic problems, as the Wrangel mammoth suffered, do we keep trying or do we let it die? Who decides? And if we succeed in establishing a population of mammoth-like animals in Siberia, what happens to them when the next climate shift occurs, or the next human conflict, or the next economic crisis defunds the project? We could not protect the original mammoths. Why do we think we can protect recreated ones? I am not opposed to de-extinction research. The science is fascinating, the ecological arguments are real, and the ambition is admirable. But I notice that de-extinction attracts funding and attention that conservation of existing species often does not. It is more exciting to bring back the mammoth than to protect the elephant. The mammoth is a story we can tell ourselves about human ingenuity triumphing over loss. The elephant is a story about ongoing failure that we would rather not hear. If we resurrect the mammoth while the elephant goes extinct, we will have learned nothing. We will have traded one tragedy for a more technologically impressive one. Perhaps the most honest thing we can say about mammoth de-extinction is that it is a symptom of our grief. We mourn what we have lost. We want to undo the damage. We want to believe that extinction is not forever, that errors can be corrected, that the dead can return. This is a human impulse, not a scientific one. Whether it leads to living mammoths or merely expensive failures, it tells us something important about ourselves. We are not at peace with what we have done. The steppe that could return. Let's return to Pleistocene Park, because it offers a vision of what might be possible without the complications of de-extinction. Sergei Zimov started this project in 1996 on a remote stretch of tundra in northeastern Siberia. His hypothesis was simple. The mammoth steppe died because the mammoths died, not just because the climate changed. If you reintroduce large herbivores to the tundra animals that graze, trample, and disturb the landscape, you might be able to recreate the conditions that once supported mammoths. The animals Zimov has introduced include bison, horses, musk oxen, yaks, and reindeer, all species that existed alongside mammoths and might play similar ecological roles. The results, after 3 decades, are encouraging. The grasslands are returning in areas where animals graze. The permafrost is colder where animals trample the snow, compacting it and allowing cold air to reach the soil. The carbon stored in the permafrost, a massive reservoir that could dramatically accelerate climate change if released, seems more stable in areas with restored grasslands. The mammoth steppe is not coming back entirely, but pieces of it are emerging, proof of concept for an idea that once seemed fanciful. This is rewilding, and it doesn't require resurrecting extinct species. It requires understanding ecosystems as systems, networks of relationships that can be degraded or repaired, simplified or complicated. The mammoth is gone, but the mammoth's role might be partially filled by other animals. Not perfectly, nothing replaces a keystone species perfectly, but enough to restore some ecological function. Enough to matter. The broader rewilding movement has applied similar logic to other degraded ecosystems around the world. Wolves reintroduced to Yellowstone changed the behavior of elk, which changed the vegetation, which stabilized riverbanks, which altered the course of rivers. Beavers reintroduced to British streams created wetlands that reduced flooding and increased biodiversity. Elephants maintained in African savannas prevent bush encroachment and maintain grasslands for other species. The pattern is consistent. Large animals shape their environments, and removing them simplifies ecosystems in ways that cascade through the food web. The mammoth steppe will never fully return. The climate has changed too much. The animals that once filled it are gone, and human activity makes restoration at scale impractical. But partial restoration is possible. Local experiments like Pleistocene Park demonstrate what could be done if there were will and resources. The mammoths cannot come back, but the world they helped create, the grasslands, the carbon storage, the biodiversity might be partially recoverable. This is not resurrection. It is something more modest and perhaps more realistic. Acknowledgement that what was lost had value, and that some of that value can be restored even without the original animals. The permafrost time bomb. There is a darker dimension to the mammoth story that connects directly to our present moment, and it involves the very ground in which their remains are buried. The permafrost of Siberia, Alaska, and northern Canada contains approximately 1.5 trillion tons of organic carbon, roughly twice as much carbon as is currently in the atmosphere. This carbon has been locked in frozen soil for thousands to tens of thousands of years, preserved by cold temperatures that prevented decomposition. As long as the permafrost stays frozen, the carbon stays put. But the permafrost is not staying frozen. Climate change is warming the Arctic faster than any other region on Earth, a phenomenon called Arctic amplification. Average temperatures in some parts of Siberia have increased by several degrees Celsius over the past few decades. Buildings are sinking as the ground beneath them thaws. Roads are buckling. Cliffs are collapsing into the sea. And as the permafrost thaws, microbes begin decomposing the organic material that has been frozen for millennia, releasing carbon dioxide and methane into the atmosphere. This is a feedback loop that could significantly accelerate global warming. The more the planet warms, the more permafrost thaws. The more permafrost thaws, the more greenhouse gases are released. The more greenhouse gases are released, the more the planet warms. Scientists estimate that permafrost thaw could add the equivalent of several billion tons of carbon dioxide to the atmosphere by the end of this century, potentially more than all current human emissions. The precise numbers are uncertain because we don't fully understand how quickly the permafrost will thaw or how much of the carbon will be released as methane, which is about 30 times more potent as a greenhouse gas than carbon dioxide over a 100-year period versus carbon dioxide. Here is where the mammoths come back into the story. Remember that the mammoth steppe was maintained by grazing animals, and that one of its characteristics was cold permafrost kept frozen by trampled, compacted snow. When the mammoths disappeared, the steppe converted to tundra and forest, which insulated the ground and allowed it to warm. The extinction of the mammoths may have initiated the first major pulse of permafrost warming at the end of the Pleistocene. We are now experiencing a second pulse, caused by industrial greenhouse gas emissions. The two pulses are related. The first made the permafrost vulnerable, the second is exploiting that vulnerability. This is Sergei Zimov's argument for Pleistocene Park, and it is not primarily about nostalgia or even about biodiversity. It is about carbon. If large herbivores can maintain grasslands that keep permafrost frozen, then rewilding the Arctic might be a form of climate mitigation not sufficient on its own, but potentially significant. If de-extinct mammoths could be established in numbers sufficient to have ecosystem-level effects, they might help stabilize the permafrost and slow the release of ancient carbon. This is speculative, of course. We don't know if it would work at scale, but the logic is sound, and the stakes are high enough that the experiment seems worth attempting. The mammoth extinction, in this framing, was not just a biological tragedy, but an early warning of climate feedback loops that we are now experiencing on a global scale. The mammoths maintained a world that kept carbon locked away. Their absence released some of that carbon. Our emissions are releasing more. The story that began with the death of the last mammoth continues today, and we are all characters in it. What the silence says. We are approaching sleep now, and I want to take a few moments to reflect on what this long story might mean not as scientific conclusion but as meditation. The mammoth lived for millions of years. Hundreds of thousands of generations were born, grew up, formed herds, raised calves, grew old, and died. Each mammoth was an individual with a nervous system, a social life, a territory it knew, companions it recognized, preferences and habits that made it unique. The mammoth was not an abstraction or a symbol or a representative of a species. It was a creature, repeated billions of times across deep time, each iteration as real and specific as you are. And then they were gone. Not abstractly gone, specifically gone. The last mammoth on Wrangel Island died on a particular day, in a particular place, from a particular cause. It was a specific individual with a specific life history. It had a mother who nursed it, siblings it played with, perhaps offspring of its own. On the day it died, there were mammoths on Earth. On the next day, there were not. The transition was absolute, and it happened at a specific moment that we cannot identify but that definitely occurred. This is what extinction means. Not a gradual fading, not an abstraction, but a final individual drawing a final breath. Every extinct species has this moment, this last one, this boundary between existence and non-existence. The dodo had it, the passenger pigeon had it, the thylacine had it, the Baiji River dolphin had it. The moment is always unwitnessed. We never know which individual is the last until long after, but it always happens. There is always a last one. I find this unbearably sad, and also somehow important to sit with. The mammoths are gone, and no amount of understanding why will bring them back. The genetic research, the climate modelling, the archaeological analysis, all of it documents a loss, not a recovery. We can know more and more about what vanished, but our knowledge cannot undo the vanishing. This is the condition we live in, surrounded by information about things that no longer exist, able to reconstruct in exquisite detail worlds we can never visit. But perhaps the knowledge is not useless. Perhaps understanding the mammoth extinction helps us understand what extinctions mean, how they happen, what conditions make them more or less likely. Perhaps sitting with the loss, really feeling it, not just acknowledging it, intellectually makes us more attuned to the losses happening now, the ones we might still prevent. Perhaps the mammoth, in its long silence, is teaching us something about attention, about consequence, about the weight of choices made across generations. I don't want to overdraw the moral. The mammoth is not a parable sent to instruct us. It is just a thing that happened, a species that lived and then didn't, a story with no author and no intended lesson. But we are creatures who make meaning, who cannot help making meaning, And if we are going to derive meaning from the mammoth extinction, let it be this: the world is not obligated to stay the way we found it. What exists can cease to exist. What seems permanent can end. The only things that persist are the things we choose to maintain, and even then, not always. The elephant in the room. We have talked all night about mammoths, but there is a living elephant that we have barely mentioned, and the omission is deliberate because the comparison is uncomfortable. The Asian elephant, Elephas maximus, is the mammoth's closest living relative. The two species share a common ancestor and diverged only about 5 million years ago, recent enough that their genomes are 99.6% identical. Asian elephants look like mammoths without the fur, the fat hump, and the enormous curving tusks. They behave like mammoths too: matriarchal herds, long-range migrations where habitat permits, complex social bonds, extended parental care. When scientists want to understand how mammoths lived, they study Asian elephants as a living model. The Asian elephant is endangered. Fewer than 50,000 remain in the wild, their habitat fragmented by human development, their populations isolated and declining. They face poaching for ivory and body parts, conflict with farmers as they search for food in shrinking ranges, and genetic erosion as populations become too small to maintain healthy diversity. The trends are similar to what we see in the mammoth record before extinction: habitat loss, population fragmentation, increasing human pressure, declining genetic health. The parallels are not subtle. The African elephant, more distantly related to mammoths, faces similar pressures. Both African species, forest and savanna elephants, are now recognized as separate species, are threatened by poaching and habitat loss. Despite decades of conservation effort and international attention, elephant populations continue to decline in many areas. The rate of loss is slowing in some regions, but the overall trajectory remains downward. Here is the uncomfortable truth: we know how to cause mammoth extinction, and we appear to be doing it again. The same factors that killed the mammoths — climate change, human hunting, habitat destruction, population fragmentation — are affecting elephants today. We have the scientific knowledge to recognize the pattern. We have the resources to intervene. We have the moral vocabulary to describe what is happening. And yet the elephants continue to die, one by one, population by population, in a slow-motion replay of the mammoth collapse. I bring this up not to lecture but to observe. The mammoth extinction feels safe to contemplate because it is over. We can analyze it, draw lessons from it, even grieve it, without having to do anything about it. The elephant extinction is still in progress. It is not safe. It is not over. It makes demands on us that the mammoth no longer can. If the mammoth teaches us anything, it should teach us that extinction is real, that it happens to species we know and love, and that once it happens it cannot be undone. The mammoths are not coming back. The elephants still have a chance if we choose to give them one. The gift of wondering. One last thought before we arrive at the end. The mammoth extinction is not a solved mystery. It probably never will be. The evidence is too fragmentary, the causes too complex, the interactions too tangled. Climate played a role. Humans played a role. Genetics played a role. Local factors mattered in ways we can never fully reconstruct. The mammoth died of multiple causes, like most things die, and assigning primary responsibility is as much a philosophical choice as a scientific conclusion. This unsolvedness is, I think, a gift rather than a frustration. We live in a culture that values answers, that treats uncertainty as a problem to be solved rather than a condition to be inhabited. But some questions are better for being open. The mammoth extinction is one of them. We can revisit it, turn it over, examine it from new angles, and find new things each time. It is not a textbook case with a definitive solution. It is a meditation object, an invitation to think about deep time, about human nature, about the fragility of ecosystems, about the ethics of our presence on this planet. The fact that we don't know exactly what happened is what makes it worth thinking about. And perhaps this is why the mammoth persists in our imagination when other extinct species do not. The dinosaurs are ancient and alien. We can barely imagine their world. The dodo is cartoonish, its extinction a punchline. But the mammoth is close enough to know and far enough to wonder about. We have its bones, its flesh, its DNA, its images painted by our ancestors. We know what it looked like, how it lived, what it ate. We know everything except the thing we most want to know. What it was like to be there when they still walked the earth, and what it was like when they stopped. So let the question remain open. Let the uncertainty be a comfort rather than an irritation. The mammoth's silence does not demand an answer. It invites contemplation, and contemplation is what we're here for tonight. A brief pause for breath. You have been listening for a long time now, and before we reach the end, let me offer a moment of stillness. Close your eyes if they are not already closed. Let your breathing settle into whatever rhythm feels natural. The mammoths we have been discussing walked the earth for millions of years, through ice ages and warmings, through the rise and fall of other species, through changes we can barely imagine. They lived without hurry. Their calves stayed with their mothers for years. Their herds moved slowly across vast landscapes, following the seasons, following the grass, following patterns of migration that had been established for thousands of generations. There was no urgency in their existence, only the deep time of evolutionary patience. We are not mammoths. Our lives are brief and fast and full of noise. But tonight, for a moment, we can borrow something of their slowness. The mammoth did not know it was going extinct. It simply lived, day by day, doing what mammoths do, until one day there were no more mammoths. There was no awareness of endings, no grief for what was being lost, no sense that an era was closing. The ending came, as endings do, without announcement. We know things the mammoths did not know. We know that endings come. We know that species disappear. We know that we ourselves are mortal, and that the species we belong to is not guaranteed permanence. This knowledge is a burden, but it is also a gift. The mammoth could not mourn its own extinction. We can mourn it for them. We can carry the memory of what was lost, even if we cannot undo the loss. This is what consciousness gives us, the ability to hold things that are gone, to care about what no longer exists, to feel the weight of absence. Rest in that knowledge for a moment. Let the weight of it settle, and then let it ease. The mammoths are gone, but you are here. The world that existed when they walked it is changed beyond recognition, but something of it persists in fossils, in DNA, in the stories we tell, in the permafrost that still holds their remains. Nothing is entirely lost. Everything leaves traces. Even extinction is a kind of presence, the shape of something that used to be there. Breathe. Rest. The end is coming, but not yet. The strange survival of ivory. There is one more aspect of the mammoth story that deserves attention, because it connects the ancient past to the present in uncomfortable ways. Mammoth ivory is legal to buy and sell in most countries. Unlike elephant ivory, which is heavily regulated or banned due to its connection to poaching, mammoth ivory comes from animals that have been dead for thousands of years. No mammoth suffers when a tusk is harvested from permafrost. No population is depleted. The trade seems, on its face, to be ethical, a way to satisfy demand for ivory without harming living animals. The reality is more complicated. The mammoth ivory trade has created a market infrastructure that can easily be used to launder elephant ivory. Elephant tusks can be stained, treated, and passed off as mammoth tusks, especially when documentation is lax and buyers are not experts. Studies have found that a significant percentage of ivory sold as mammoth is actually elephant. The legal mammoth trade provides cover for the illegal elephant trade, allowing poachers and traffickers to move product through channels that would otherwise be closed to them. There is also the question of what the mammoth ivory trade does to the scientific record. Tusk hunters in Siberia are incentivized to extract as quickly and profitably as possible, often destroying the context that makes specimens scientifically valuable. A tusk found in situ, with associated bones and sediment, can tell us about the animal's life, death, and environment. A tusk ripped from a riverbank and sold to a dealer tells us almost nothing except that it is ivory. The commercial value of mammoth remains is actively destroying their scientific value, which is a kind of extinction in itself, not of the animals, but of the knowledge they could have provided. And there is something troubling about the trade at a deeper level. The mammoths are gone. Their bodies, their tusks, their bones are all that remain. To turn those remains into piano keys and jewellery and knife handles is to reduce the last physical traces of a species to commodities. It may be legal. It may even be, in narrow terms, ethical. No living animal is harmed. But it feels like a final indignity, a failure to recognise that some things should be treated with reverence rather than price tags. I do not have a solution to this problem. The mammoth ivory trade provides livelihoods for people in remote regions of Siberia. Banning it would not necessarily reduce demand for ivory. It might simply shift more demand to illegal elephant sources. The ethics are tangled in ways that resist easy resolution. But the trade is worth mentioning because it reminds us that the mammoth extinction is not over. It is ongoing, in the sense that we are still deciding what the mammoth means to us, still negotiating our relationship with the dead. The mammoths cannot speak for themselves. We speak for them, and our speech is often about money, a meditation on tusks. Let me tell you one more thing about tusks, because they carry meaning beyond their commercial value. A mammoth tusk grew throughout the animal's life, adding layer upon layer of dentin in daily and annual cycles. The tusk recorded everything: periods of plenty and periods of scarcity, seasons of migration and seasons of rest, moments of stress and moments of calm. Scientists reading tusk layers can detect when a mammoth gave birth. A distinct chemical signature marks the event. When it fought with another mammoth, damage patterns in the tusk. When it experienced drought or cold or disease, changes in the growth rate and mineral composition. The tusk is a diary, written in ivory, spanning decades of a single animal's existence. The study of Kik, the mammoth whose life we discussed earlier, revealed that he travelled enormous distances over his 28 years, the equivalent of circumnavigating the globe twice. But the isotope analysis also showed something more subtle. His patterns of movement changed as he aged. When he was young, travelling with his mother's herd, he stayed in a relatively limited range. After reaching adulthood and leaving the herd, he began to roam more widely, probably in search of mates. In his final years, his range contracted again, as if age or illness was limiting his mobility. The tusk recorded not just where he went, but how he aged, how his capabilities changed, how he slowed down as death approached. There is something almost sacred about this level of knowledge. We know more about Kik's life than we know about most humans who lived 17,000 years ago. We can trace his footsteps across Alaska, season by season, year by year. We can infer his relationships, his challenges, his probable causes of death. And yet we will never know what it was like to be him, to experience the world through mammoth senses, to feel mammoth emotions, to think mammoth thoughts. The tusk tells us everything except the thing that matters most, what it meant to be alive. This is the gap that all science faces when studying the dead. We can reconstruct bodies, behaviours, environments. We can trace lineages and migrations, map genomes and measure isotopes. We can know, in extraordinary detail, what something was, but we cannot know what it was like. Consciousness leaves no fossils. Experience dissolves at death. The mammoth's inner life, whatever it was, ended with the last mammoth and cannot be recovered. Perhaps this is another reason why de-extinction fascinates us. We want not just to bring back the mammoth's body, but to somehow recover its experience, to know what we lost when we lost it. But even if we create a mammoth-like animal, it will not be the same as the mammoths that died. It will have its own experience, its own consciousness, its own inner life that we cannot access. The gap between knowing about and knowing as cannot be bridged. It is part of what makes other beings other. Rest with that mystery. Let it be unsolvable. The mammoth's experience is gone, and ours will follow eventually. What matters is not the recovery of the past, but the attention we pay to the present. The mammoths lived fully in their moment. We can do the same in ours. Closing. The mammoths are gone. They have been gone for 4,000 years, or 10,000 years, or 12,000 years, depending on where you draw the line and which population you count. The world they inhabited, the mammoth steppe, the Pleistocene megafauna, the great herds moving across continents, is as vanished as they are. What we have instead is bones in permafrost, images on cave walls, stories that we tell to make sense of loss, and a vague unease about our role in what happened. I do not think the mammoths would care about our guilt or our grief if they could know about it. The dead do not care about the living's feelings. That is one of the things that makes death so absolute. But we care. We cannot help caring. The mammoth extinction is our first extinction, the first time humanity might have contributed to the erasure of another species, and it marks us in ways we have not fully reckoned with. We are the species that outlived the mammoths. We are the species that might have killed them. We are the species that remembers them, imperfectly, across the gulf of millennia. And now, perhaps, we are the species that might try to bring them back, not because we can undo what was done, but because we cannot accept that it was final. This is either the noblest impulse in human nature or the most arrogant, and I honestly do not know which. Maybe both. Maybe the mammoth's final lesson is that we are complicated creatures, capable of destruction and mourning and ambition and care, all at once, often in the same act. The mammoths walked this earth for millions of years. They watched the glaciers advance and retreat, the forests rise and fall, the landscapes transform and transform again. They were not observers of these changes, but participants in them, shaping the very ground they walked on. And when they disappeared, the world changed in ways that are still unfolding in the vegetation that replaced the steppe, in the permafrost that began to warm, in the cascade of extinctions that followed their loss. The mammoth was not just an animal. It was a force, a presence, a weight on the earth that is now gone. We feel that absence, even if we don't always recognize it. The world we live in is a world without mammoths, without the ecosystem they created, without the balance they maintained. We have adapted to this world because it is all we know. But the bones remind us that it was not always so, that something larger and stranger once existed, that the past contained possibilities that the present has foreclosed. The mammoth is a window into a world we cannot enter, and a mirror reflecting what we have lost. Sleep now, if sleep will come. Let the mammoths walk through your dreams as they once walked through the world, huge and slow and silent, their breath misting in the cold air, their footsteps shaking the earth. They are not there, of course. They have not been there for a very long time. But imagination is the only time machine we have, and tonight, for a moment, the mammoths can live again in the space between waking and sleep. They waited a long time to be remembered. They can wait a little longer. The silence they left behind is not empty. It is full of questions we are still learning how to ask, full of lessons we are still learning how to hear. The mammoths do not speak, but their bones speak for them. Their DNA speaks for them. The cave paintings speak for them. The very landscape speaks for them, transformed by their absence into something it would never have been if they had lived. Listen to that silence as you drift away. It is not nothing. It is the sound of deep time, of species that lived and died, of worlds that existed and vanished, of the great wheel of life turning and turning across millions of years. The mammoths were part of that wheel. So are we. The wheel keeps turning even when we sleep, even when we forget, even when we pretend that we are somehow separate from the pattern. We are not separate. We never were. The mammoth extinction is not ancient history. It is our history, still shaping the world we live in, still asking questions we have not yet answered. What do we owe to the species we share this planet with? What responsibilities come with the power to cause extinction? How do we live in a world where loss is permanent and consequences ripple across generations? The mammoths cannot answer these questions. They are gone, but we are still here, and the questions remain. Perhaps that is the mammoth's final gift. Not answers, but the questions themselves, questions that matter, questions that shape who we become, questions that connect us to the deep past and the uncertain future. Sleep now. Dream of mammoths if you can. And when you wake, remember that the world you wake into was shaped by their absence, as it will someday be shaped by absences we cannot yet imagine. The present is built on loss. It is also built on what survives. Both are true. Both matter. Both deserve our attention. And that perhaps is the closest thing to immortality that any of us will ever know.